Hello everyone, welcome to day 8 of AI system design session. The use case is semantic layer generation using AI agent. So till now we learnt about, we took the use case, that is the semantic layer generation, and then from there we performed some capability discovery. In that session we discovered, okay, whichever the complete, when we analyzed the complete process, whichever steps can be converted as autonomous AI agentic operations and which can be deterministic, and those should remain as is, whether performed through some kind of existing tools like currently it is happening, or some involvement of the human in the loop for review approval process. And then next again we evolved with the domain driven architectures, event architectures, then again the state schema evolutions, how to design the land graph state schema. Then again we discovered about the planner agent, how the planner agent works and what are the different memories, context engineering, all this. So now we can say like that, okay, our agentic AI system is ready with the development process. But what will happen, how to control its behavior after 6 months? So that is what it's called, that after 6 months when it gets productionized, we see lots of technical debts. That means it fails in many scenarios. So currently the system is ready in the development environment, but how to make it the actual enterprise ready agentic AI system that will work seamlessly, scalefully manner in the production environment. So we have to address some of the technical debts. So new concepts that we are going to learn. The first one is about the service ownership. The second one is about the contracts between the service. Third one is the failure isolation, and fourth one is the architectural debt or the technical debts. Okay. So in this, what I can say is that because the architectural debt, it does not usually come from choosing a wrong LLM, but in fact it comes from various factors. For examples like the unclear service ownership and the database, there should be if there is a shared database, and then duplicate business rules, undocumented contracts, not only documented contracts. If these contracts are only documented in the system design spec and resides into that one without enforcing the actual use of all these contracts. When I say contracts, there will be different kinds of contracts, right? Event contracts, communications, all those communication contracts, how these services they communicate with each other, right? So it is designing as well as enforcing. When we enforce, then only the actual real picture where it fails, those comes into the picture, and there we have to address all those pain points, all those slick points, right? And then the next one is about what are the different factors causing these technical debts. I'm talking about the agents directly calling each other. No, there is no separation where we can call the synchronous operations and asynchronous operations, and some uncontrolled schema changes happens. And also the planner agent that we had designed last time, when we keep on, because we had also said that in our scenario this is a deterministic planner agent instead of introducing some LLM. So very deterministic for addition of new kind of business logic, means what scenario it will plan, how the activity, the next action, how it will plan. So definitely we are including more and more business logic into that one. So at certain point of time, what happens, no, that single planner agent, which looks very simple during the starting point, it becomes a giant ball of all accumulated business logic. So how to make it distributed instead of a monolithic planner agent? So all these factors are responsible for this technical debt, and now we are going to learn how we can do this. Again, I am telling you that this is just one part of understanding how we can do. This is not enforced and adhere to the principles of, in some cases like the planner agent, we had decided that no, it should be deterministic, and what scenario this can be deterministic, that also we had discussed last time. So all these architectural principles I am discussing, those are not applicable only for this use case, but instead these are applicable to design any kind of agentic AI systems, there might be some kind of 10 to 15% variations depending on the business logic use case, whether something can be probabilistic, some operations can be deterministic, how this can be done, right? So let's start with the first principles, that every capability needs an owner. So when I say that the service ownership, so you might have remembered that in our previous sessions also we had discussed about bounded context, right, in domain driven design. So what we had done during that time we were discussing about the two probabilistic areas, ambiguous areas where we have planned for our AI agents. Okay, the first one, which is completely deterministic, that is the metadata service. So instead of inside that metadata service, what are the different operations can be performed? It's like DDL ingestion, schema profile, schema parsing, profiling, and then glossary source, schema versioning. All these operations could have been done. And the next one, that is the ontology service. Inside that one, extracting the business concept, the business mapping, the relationship, semantic reasoning, etc. And the third one is that governance, ontology governance, where it is happening some validation, confidence thresholds, approval, human in the loop, review, and then compliance metadata, publication, authorizations, all those. So all these service, when we say that these are the service and inside that all these operations are getting performed, so we should have a very clear boundary, usage boundary, who should be the owner of all these services and where the data resides. So it is like the service don't share any ownership just because they need to access the same information. For example, ontology service may need metadata, right? And that does not mean it owns the metadata. It consumes the metadata through a contract, right? So these distinctions, even though now when we are discussing, that looks very small, but when the system grows, one of the biggest difference between a maintainable enterprise platform and a distributed monolith, this is the way we have to make it more microservice based. Okay, who should own, who should consume, who should publish, who should consume, how should be the contract, and the contract should be based upon the consumer requirement and how that can be enforced. There should one kind of validation should be performed by the publishers before publishing the contract to the consumer. The consumer, any service, if there is a one schema is already the schema of the contract I am talking about, that is already published, and the others service came, so based upon its need it can add some status, some event, okay, but it cannot rename its existing column in the JSON contract file. And for that, when it is adding one more, so one kind of schema versioning should happen, right? So all these things should be adhered as part of the service ownership. So if I talk about the contract, then definitely this kind of contract, what is the event? When I say that event driven architecture, so what should be the contract between the consumer and the publisher? That is well defined in the JSON format. In case of any kind of update, for example, schema updated, some kind of new validation request raised, those can be added as a new functionality. So how this happens, how this gets maintained? Through a schema registry. There that registry should be reviewed and approved by both publisher and the consumer applications. Any kind of update needs to be there, that should be completely version controlled. That should be that should be controlled by some versions. And yes, so this is about the contract, the registry, schema registry and the contract. The next one, if I am talking about the failure scenario. So when it comes to the failure scenario, for example, there are 4 kinds of services are there. So first is that for the graph, knowledge graph systems, we are having Neo4j. So when the Neo4j request, the Neo4j system fails, what we can do is that it the new request when it comes, some kind of schema validation, some schema understanding, when it comes the new request, that should goes into a queue. The existing already processed information, those are getting saved in the PostgreSQL. So when the request for the existing process request, already processed information request comes, then that should be suffice, that could be served, that is the present, the data is already present inside the PostgreSQL. And if some new request is coming, that should go in a queue. So in that way we can protect the failure. Second one is that vector DB. If the vector DB is failed, so in that case, okay, perform some kind of keyword based search or perform some kind of graph traversal search that is supported by the graph DB, vector DB, Neo4j, graph DB, Neo4j. And third is that if some LLM is unavailable, yes, you can put second or third LLM, but if complete LLM is unavailable, so in that case we can go to the deterministic rule based applications, rule based suggestions. And the fourth one is that cannot be avoidable, that is the Kafka. So we should have that minimum SLA in order to make the system alive all the time. So this is the failure isolation. That means if one component is failed, then it should not impact the rest of the components of the complete system. Instead of that one, how that failure can be isolated and how that request can be served. This is the concept of the failure isolation. So when we are writing any kind of code, basically what happens, this Kafka stream, it is consuming. So what happens? We keep that some kind of retry operations within some try and a catch block. But instead of that one, we should keep in this circuit breaker. So circuit breakers means it immediately, when some component is failed or it is unable to serve the request, it immediately fails the taking the next request in the queue, so that it avoids keep on piling the number of requests one by one in the queue. Instead of that one, it immediately, when it immediately comes back, it starts serving the new request. So these are the few ways how we can handle the failure isolation. Now come back to your planner. Okay, so we had designed our planner in a deterministic way. So that is having some kind of if-else kinds of rules defined. For example, if I have defined like that def route artifacts, okay, and if the confidence is less than 0.7, then we have to validate that. And if it is like something domain is related to finance, then extra validation, because finance needs some kind of extra validations. Okay, if the ontology version is greater than 4, then run some kind of evolution. So these are some kinds of tags, those are planned by the planner, and as it is deterministic, we have maintained that through some kinds of rules directory. So as the system grows, there will be hundreds of business logic needs to be validated if else through the if else conditions, and the planner will plan accordingly. So in that case, what will happen, that the logic of the planner will get blotted and blotted. So what will happen, this monolithic application will not able to perform as per the expectations. Okay, so we have to break it down. So what we will do, we have to make all these policies, all these rules, those are the kind of policies, those we have to shift all those policies to a policy agent. Okay, so kind of this kind of raw policy, that rego policy, we have to maintain the way it access. So in that case, we have to just planner a simple code we have to put here. Route, under what condition it will route. Artifacts means it contains the information about all those tags, the complete workflow. So it is policy engine, we have created one policy engine, and that is from the governance perspective, that we have completely isolated from this complete code, the code of the planner logic, and that should be getting reviewed. That should be, you can say, like authored or reviewed and approved by some SMEs, some governance people, okay, who are governing the complete all these business rules. So that should be, we are isolating that, keeping it to a separate file itself, and that is policy engine, okay. And policy is maintained in the semantic routing / v3. Its version is something v3, and inside this semantic routing v3.rego, this is maintained in the rego format, owned by the governance, not by the planner team. Okay, so package semantic routing, and there we are maintaining what should be the next action is equal to human review when the input dot confidence is less than 0.7. When it is input dot domain is equal to finance and input dot confidence is greater than 0.7, then in that case some extra validation is required. So what should be the next action for all kind of rules? Everything is maintained inside this semantic routing file, that's a separate file, and that should be in the .rego format, the agent policy. So this is about how we are making the planner agent more modular, distributed as compared to a single monolithic system. So we have covered all these systems. Now the next question is that, okay, for this contract enforcement I was talking about, instead of just retaining inside the design doc, we have to make it enforcement. So when happens, now every event schema, for example, schema ingested and validation ambiguity detected. So all of them gets registered inside a schema registry, not just written into Kafka topic and hoped for something. The registry is configured with the compatibility mode, and for this platform we use the backward compatibility. A new schema version must be readable by consumers still running the old schema version. Okay, so that means the metadata service, for example, the metadata service can add a new optional field to schema.ingested without breaking anything downstream, but it cannot rename. The schema has to contain has without registry itself is rejecting the deployment. Okay, the registry becomes a continuous integration gate. It will be not wiki page, okay, add all this information into that one. It will enforce what can be possible, what cannot be possible. Consumer driven contract testing. So before ontology service ships a change to how it consumes schema.ingested, and before metadata service ships a change to how it produces it, both run a shared contract test. Okay, so where the consumer publishes what it actually expects from the payload, and the producer CI pipeline runs that expectation against its real output before merge. And this catches the exact failure the original script described. That is column name silently becoming physical column name. It should not be. It should be prohibited. Okay, because that contract has been agreed between the publisher and the consumer, right? And the next one is about explicit deprecation policy with a forced sunset window. So when a contract genuinely needs a breaking change, it's a like version 1.0 to 2.0. So both versions run in parallel on separate topics for a defined window. For example, 60 days. Generally, we take 60 days of time period. Consumers migrate on their own schedule within that window, and the old version is only retired after the telemetry confirms 0 consumers remain on it. So we used to get email and from the different teams that okay, you migrate to the newer versions, right? We have to enforce that okay, our systems is adhere to the newer version. So no breaking change ships as a silent override, ever regardless of how urgent it feels at the time. Okay, so and the next one, before concluding this session, let's discuss let's conclude, just refresh our mind. what we discussed, what are the various checkpoints before designing this architecture addressing all these technical depths. So for the first question is that who owns the data? Okay, the single service, if we say that no, there is a multiple services, multiple states are owning the data, no, that is not correct. Okay, we have to revisit and we make that there should be clearly defined which service should own the data. So how we have to verify it? Some kind of ownership document we have to maintain and we have to adhere, enforce that. Second question is, what is the contract? Contract means whether contract means, are we saying about the shared database? If it is, then we are doing the wrong thing. Okay, it should be event. What should be the publisher and the consumer? What kind of information should be communicated between them? It should be compatible with both the applications. So how we have to do some kind of version schema registry. Third is that can we change it safely? Some kind of contract CI test we need to do. Then what happens if some dependency fail? So we have to do some kind of game day test or cloud test we have to do. If this can be dependency, for example, we discussed about the dependency of Neo4j, VectorDB, LLM, then Kafka, all these, how we have to address those kind of failure scenarios that we have discussed. Okay, next is that can we replay the workflow? That must be done, and replay the historical events. We should get all the idempotent results. Can agents deploy independently? Definitely, this should be done. Independent CI/CD should be performed. Can we explain an old decision? Explainability is much required. We should have enough provenance gateway, and provenance cross policy version should be maintained by our applications. So here, what we can say, every capability needs a clear owner. Services should communicate through explicit contracts, not shared database schemas. Kafka provides event transport, but event contracts provide compatibility and governance. Failure boundaries matter, and LLM outage should not stop deterministic metadata ingestion. Every important AI decision needs traceability provenance. So what we learned is that the real test of an enterprise AI architecture is not whether you can draw it, you can confine it inside the system design document, but instead it's whether you can prove it contracts, isolate the failures, replay its histories. Replay its history means idempotent system. Okay, each time you replay, the same response should come and evolve without breaking the system. So that is the actual designing one AI agent system that should work in a very scalable, trustworthy manner in the production environment. So tomorrow in day 9, we are going to learn how the complete system we are taking the architecture, the complete system architecture that we have designed till now, that into the production. So how each service is going to one kind of Docker and then Kubernetes to with the AWS environment system, that is again EKS system, then CI/CD. There should be how the secrets will be getting managed, auto scalings, and the observability systems. So see you tomorrow. Stay tuned and happy learning. Thank you.